Hi everyone, I'm Gaurav Sant. I'm a professor of engineering at UCLA. I'm going to talk to you about decarbonizing cement production and concrete construction. We're going to talk a little bit about CCUS, carbon capture, utilization, and storage, what this could mean for the sector. I'm going to try very hard not to bore you for the next 30 minutes. So I'll open with sort of saying the most important thing. I count on concrete, you should too. Important to reiterate this over and over again. We produce about 5 billion tons of cement, about 25 billion tons of concrete. It's not going to go anywhere anytime soon. The question that we really want to try and ask is, why has this been so successful? Really based on cost, abundance, open time, really forgiving material, incredibly compatible with steel. And we've been able to exploit the hub and spoke model that's been able to give us incredible economies of scale around production. Right? This is really quite important, because if you think about why we've been able to do this, you can produce cement using limestone, which you find effectively all around the world. Couple of things to keep in mind. While the economies of scale are great, your ability to actually do much with the concrete once it gets mixed is really quite small, right? It's all basically passive, which means that once the material's mixed, there's no further interventions that are possible. The materials societally required and necessary, you're not going to get away from it anytime soon. Think about a world without concrete. That world's actually really hard to imagine. Actually, almost demands going back to the caves or living in trees, something along those lines, which I don't think we really want to do. Important to sort of focus on what is the Achilles heel of cement production, right? So the Achilles heel is really quite simple. We take limestone, we burn it in a cement kiln to get calcium oxide. You release CO2 by the thermal decomposition reaction. Why is this important? Effectively, limestone's calcination makes up about 65% of the process emissions. The remainder 35% of the emissions come from heat that is needed for the cement kiln. Now, this is actually quite important, because you want to keep this number in mind really closely. Because even if you completely decarbonize all of the heat that's needed for cement production, you will never decarbonize the process, right? And this is really important, because it really tells you what you should focus on, which is really the process emissions associated with limestone's decomposition. Now, keep in mind that, while you can indeed do things like switch fuels, you can even imagine sort of the extreme scenario that you're going to burn hydrogen to produce heat in a kiln. You actually will not get rid of these process emissions. So if you want to think about cement decarbonization, the focus has to be really on process emissions. That's the number one step. So why is concrete and cement decarbonization so hard, right? There's a couple of ways of looking at it. You can do what McKinsey has done and said, let me try and look at this in terms of what is the sectoral contribution of cement in terms of CO2 emissions, somewhere between 7, 8, 9%. But really, I think what makes sense to look at is actually this number right here. Kilograms of CO2 per dollar of revenue, right? I think this is a really important one to be looking at, because if you compare cement to just about anything else, you put out a whole lot of CO2 for, in fact, a really low revenue in terms of product, right? So this is an important thing to focus on, because this tells you why it actually is really hard to decarbonize cement production. It's really based on economics. Now, if you look at sort of the cement decarbonization roadmaps, there's sort of a variety of them around, right? So there's some version of this floating around from the IEA, from the GCCA, from whoever else that you can imagine. Effectively, it really breaks down as follows, right? So I'll come back to the biggest part of this later, but there's reduction of clinker to cement ratio. As an example, this is something that Karen just spoke about how you can actually do substitutions. There's fuel switching. Look at, for example, replacing a fossil fuel with something like hydrogen, if you really wanted to be pretty extreme about it. Look at thermal energy efficiency. I would actually argue that this one's great, but actually really hard. New cement plants are highly optimized. You're running at pretty close to thermodynamic efficiencies. It's not going to get a whole lot better. Electricity, I would not really focus on a whole lot. If you come back up to this innovative technologies piece, this one's actually really important to focus on, because what this one actually includes is things like carbon capture. And the expectation is the vast majority of decarbonization is going to come out of innovative technologies, right? What these are, not really clear. Might include carbon capture and storage. I'm going to talk about this in just a second. But really, you can think about it in a couple of different ways, right? So things that are mature. Fuel switching towards lower specific CO2 emissions, relatively mature. You can start to switch things out. In certain cases, supply may be limiting, right? So you can start to think about doing substitutions of cement. You might be able to do it with things that are really abundant, might not work all around the world. You've got to think about affordability. Carbon capture and storage, as things stand today, is basically unaffordable. I'll talk about this in just a second. And this is basically more than 50% of the solution that's expected to be relevant to the sector. Finally, you want to look at process heat. And process heat is important, right? Imagine that you could use, for example, solar thermal heat or hydrogen to run a cement plant. You don't get rid of the process emissions that I spoke of. Really important, because you don't decarbonize cement production that way. You decarbonize a nice chunk of it, but not all of it by any means. So really, I think we want to take at least a step back and sort of ask this question: what is carbon capture, utilization, and storage, right? These words are thrown around all the time lately, right? You hear everybody talk of them. The question is, what does it imply? It implies the capture of CO2 from an emission stream, going all the way from 3%, 3% is a natural gas stream as an example, going to more than 50%, that's the type of stream that you'd get at a refinery or an ethanol plant as an example, or even the atmosphere. The thermodynamics are clearly linked to the entropy of demixing CO2 from a mixture of gases, right? So the question that you're really trying to ask is, how do I pick out CO2 one at a time and separate it from everything else that there is in the gas phase? The energy demand is linked to concentration. This is super important because the more concentrated the emission source that you have, for example, at a cement plant, it's about 20%, 25%, give or take. There's about a 10% increase in energy from atmospheric to point sources, right? This is, again, a really important thing to keep in mind, because if you can do capture with a point source, go ahead and do it instead of needing to do it with the atmosphere. It requires solid sorbents or liquid solvents, right? Could be things like MOFs, right? Metal organic frameworks, could be things as simple as sodium hydroxide and potassium hydroxide solutions. These will suck up CO2 as well. The major energy demand is all linked to the desorption of CO2. It's not the absorption of CO2, it's the desorption of CO2. And this is actually quite important, because that is actually what determines how much energy you need for capture. Keep in mind, capture is not a single process. It implies a process train, right? So you've got a pre-treatment process, as an example. You've got absorption and desorption. You've got compression. You've got dehydration. You've got pipeline transport. You've got injection into a geological formation and long-term monitoring. When you think about this process train, this is actually a really complex process train. Make no mistake. And obviously, you can see there's lots of pieces to it. If you imagine that we succeeded doing this at steady state, capture and storage is going to cost somewhere in the vicinity of $70 at least per ton of CO2, much likely quite a bit more, right? What does that mean? Amongst friends, for cement, for every ton of cement you produce, you've got to add another $70 at least, because that's the incremental cost that you're looking at. What it requires in addition is energy, right? You need thermal electric energy, ideally the non-fossil fuel variant. You need storage that comes from either an oil and gas reservoir, a saline aquifer, or the oceans. And you need permits. You need wells, you need pipelines, and you need a permit to be able to do this. These are all important things to be keeping in mind, because this is all that you need to actually do geological capture and storage, right? So whenever we throw around the idea that we're going to do CCS for cement decarbonization, you want to think about all of these things right here, right? Now, keep in mind, in addition to the CCS, there's often this U that shows up about why we should utilize CO2. There's a lot of work that's been done in this area. There's been sort of a series of National Academies reports that have looked at this. You can use CO2 to produce materials and products, right? So there's a really good report from the National Academies from 2020 that talks about this. It emphasizes durable utilization pathways, right? So you want to think about how you can put CO2 into things like cementing agents and plastics and polymers. You don't want to focus really on short-term uses, right? So don't focus on fuels, because the moment you combust a fuel, you put all of that CO2 back into the atmosphere. You want to think about technical potential. Technical potential is really important to think of. So think about every material that we make as a society, right? If you replace the central atom in every single one of those materials by a carbon atom, that tells you what the technical potential looks like. And depending on where you land, the technical potential is somewhere in the vicinity of about 3.5 billion tons. That's the largest quantity of CO2 that you could use. And the vast majority, in fact, is in building materials. Why? It's really driven by reaction thermodynamics. Mineral carbonation, the idea of taking CO2 in the gas phase and turning it into a solid, is really the only energetically downhill pathway for the utilization of CO2. Really important thing to keep in mind. The other thing that you'll often hear is that it's a function of oxide composition, right? So having calcium and magnesium in an alkali, so to speak, around is great, but the kinetics matter. Thermodynamics is wonderful, doesn't always tell you everything that you need. I'm going to talk about an example of calcium hydroxide in a couple of slides. But keep in mind, construction could be a major user of CO2, right? Why is that? Because you could take CO2 from point sources, you could take CO2 from biomass or from air capture, and you could actually use it to produce carbonate-based building materials. This is an important thing to keep in mind, because the vast majority of the realistic technical potential actually sits in construction-based systems. So think about scale compatibility. Scale compatibility is super important when you think about decarbonization. The industry dilutes clinker and cement with SCMs, right? So there's code and materials-based limits on how far you can go with this. we can use all kinds of things, right? We can use fly ashes, we can use slags, we can use calcined clays. General idea is you're trying to initiate some sort of a pozzolanic reaction to produce CSH and the AFM, or the layered double hydroxide style of compounds. Keep in mind that this is often proposed as an approach to reduce the embodied carbon intensity of cement. This is a false premise. This is simply not true. Here's the reason why. You're not changing the carbon intensity of producing the clinker. You're diluting the clinker with something else. And there's a big difference in these two things. So on a per unit basis, you're definitely reducing the carbon intensity of the binder, but you're not changing the carbon intensity of cement production itself. So dilution definitely reduces ECI, right? So no question about that. And you want to think about this really closely, because when you think about SCM replacements, you want to think about SCMs that can be processed in the most amenable, simple manner, so that the incremental carbon intensity addition that comes from the use of the SCM is as small as possible, right? So what is an ideal SCM? If you could go and dig a ditch, get something out of the ground, that would be a wonderful SCM. There's not many like that, but it's something to keep in mind. Emerging solutions, super important. Calcined clays, super important. But unless the clinker factor, until the embodied carbon intensity of clinker production itself is reduced, emissions will continue to go up. So the reason for this is really quite simple. If you look at upcoming demand in Asia and Africa, we're going to continue to need more and more and more and more cement. To imagine that we're going to be able to achieve the decarbonization demand that we have only with replacements is obviously not going to happen. And this is where all these innovative technologies start to become really important. Because without these innovative technologies, you cannot actually get away from the baseline carbon footprint that's associated with clinker production. So what complicates cement decarbonization? I think it's good to sort of take a step back and think about this. There's a couple of things that start to become important. It's a commodity sector with a commodity mindset, which means that inherently there's an aversion to risk, there's an aversion to innovation. There's building codes and standards that reward the status quo. Often this is based on a false premise of safety, but it also includes cartelized business practices, right? This is an important thing to keep in mind. You want to think about the fact that, you've got hostage downstream users. Hostage downstream users are really important because they can only build with what they are supplied with. And so long as you're in an environment of the L1 bid, the lowest bidder wins, effectively, cost is important. This is also really important because, today there's really a fundamental lack of scalable solutions. I think we should not forget this for even a second. And we have to keep in mind that we've developed over the last 150 years enormous industrial comfort in using OPC-based materials, right? So to get away from this overnight is obviously very hard. And you've got to keep in mind, it's about scale. We produce about 5 billion tons of cement. This industry alone is sort of the third largest emitter in the world. You're not going to be able to sort of change this overnight. And so the question is, what is really the pathway around having a decarbonized business is an important question to ask. So what efforts are currently ongoing? There's a lot of stuff going on. I think some of it has been touched on already. There's lots of work ongoing with cement replacement, with clinker factor reductions, with fuel switching, with the development of alternate SCMs. There's lots of technology demonstrations going on across TRL levels, so technology readiness levels, around carbon capture and storage, around electric kilns, around calcium looping processes, around CO2 separations, around oxy-combustion, all great. If you think about what these are, though, for the most part, is you're essentially saying, I'm going to try and tackle everything except the fundamental CO2 emissions associated with limestone's decomposition, right? So a different question to be asking is, are you really tackling the fundamental question at hand? The answer is probably not. Are you addressing the problem? Definitely are. But you're not really focusing on the fact that it's limestone's decomposition to produce calcium oxide, which you need to produce the cement. That's really sort of the issue at hand. The last thing to point out is that, a vast majority of these efforts are not well suited for brownfield sites. So it's very hard to go to an existing cement plant and to be able to make some of these changes trivially. That's an important thing to keep in mind, because if you can't do this at brownfield sites, it becomes hard for the industry to be able to adopt it, globally speaking. So, we did a bunch of work in the area trying to think about decarbonization, trying to think about what are all of the things that could be done, right? So there's things like data-driven efficiencies, there's low-lime cements, there's SCMs and clinker dilution, there's things like producing calcium hydroxide as an alternate feedstock for cement production. So we looked at this in sort of an interesting way. What we were focused on is really looking at solution pairs. So is there really opportunities where expanding sources of renewable energy allow you to take up CO2 into carbon sinks? We asked a question around circular economy, looking at really amplifying the use of waste from industrial, biological, municipal, and from mining operations, and looking at eliminating a dependence on CCS. Because the idea of CCS is that you don't want to force fit a one-size solution, so to speak, on an industry that has potentially a high inertia implementation, because CCS might not be well suited for many, many cement plants. We went through this and tried to look at it in a slightly different way. We're trying to think about, how do you try and approach this? So we just spin out a couple of companies that actually do work in these areas. I'm going to talk about two of them as we go through. One of them is a company called Concrete AI. The other one's a company called Carbon Build that you're going to hear about this afternoon. And we looked at a variety of other approaches really around, could we try and replace or displace limestone as the primary feedstock that you use to produce the cement? We looked at had an emphasis on three mandates, so to speak. One was eliminating the need for calcium carbonate's decomposition. We're thinking about drop-in feedstock replacements or displacements, right? So getting away from limestone completely, as an example. Looking at process intensification by electrification, so essentially using electricity instead of thermal heat was a really important question. And then looking at scale relevance and cost parity to OPC, right? We went through this process and sort of came up with a few critical considerations. And the critical considerations were, what is the incremental abatement cost of CO2? Incremental abatement cost, super important, because if you can't map this and it's not an absorbable number, you'll never do it. Looking at a timeline to deployment, we were really focused on a 1 decade long horizon. A decade long horizon turns out to be important. And we looked at the role of CO2 pricing on techno-economics. And what does that mean? What's the role of legislation, right? Legislation that either prevents emissions or taxes emissions, either ways that you look at it. And there's a couple of questions that sort of emerge from this, but really economies of scale. Is this needed? Is the hub and spoke model needed? Or can you look at decentralized manufacturing, which is becoming increasingly common? Does the future imply small footprint plants, was really the question that we were trying to ask. The next question was, how do we ensure NPV, net present value parity with OPC and OPC-based concrete today? NPV parity turns out to be super important. And then looking at sort of synergies, right? How does mineral carbonation fit into the overall carbon to value economy? And is there something to be done that actually stimulates this? Were the other questions we were trying to ask. So we went through the process, sort of landed on the other side of it. Couple of things that came about. So of course, concrete production is empirical or experimental is sort of one of the things that came out from this. Why? The heterogeneity of materials makes prediction of performance difficult. The reason that this is important is because, in effect, it doesn't matter where in the world you are, every concrete that we produce is over-designed by a factor between 20 and 200%, right? So the question is, how do you pull back this over-design is one question. Concrete proportioning is slow, empirical, and laborious. There's a mixed design that's been sitting around. You're going to incrementally tweak it. Great. But it's slow. And uncertainty in performance results in duplicated safety margins, right? So the concrete producer adds some in, the structural engineer adds some in. And so you've got sort of these replicated safety margins that come up. If you can start to pull these back, this turns out to be really important because you can start to reduce cement use by achieving better material efficiencies. So we did spin out a company that actually works in this area. As an example, on a carbonating surface, calcium hydroxide actually carbonates to completion. You get an exchange reaction of hydroxyl for carbonate. You produce water on the surface, the water auto-catalyzes the reaction, and you're able to take the reaction to completion in a matter of hours, right? So 24 hours, you can essentially take the reaction to completion. We were focused on 24-hour periods. Why? When you think about precast masonry, we were thinking about how long does it typically take to go through a process of the sort. And 24 hours turns into a really sort of nice number to be working with. Also allows for a really solid basis of measurement and verification. You can start to exactly measure how much CO2 you've taken up. Standard thermal analysis allows you to do this by sort of having strong baselines with what your materials look like before you started carbonating, what your materials look like after you carbonated them. You can start to get really strong complete mass balances around how much CO2 utilization you get. So where does this all end up? Carbon Build, which is now in the midst of commissioning its first plant, can go out and produce concrete block like this, which essentially is equivalent in terms of performance, equivalent in terms of cost, and has a carbon footprint that's 70 to 100% lower, right? Kamini Tran is going to speak about this in the afternoon, so you can sort of ask her all the hard questions. We pivoted back a little bit and sort of said, let's go back to looking at this fundamental question around limestone's decomposition. And where we landed in the midst of this was really trying to think about what other calcium oxide source could you think of that you could use to produce a Portland cement. You quickly land on calcium hydroxide. Why calcium hydroxide? When you burn it, it only releases water. That's really quite good. So you get rid of all of your process emissions. So the question is, how can you produce calcium hydroxide at a large scale? So it's something that we've worked on for about a decade now. This work has been funded by the Department of Energy. And really what we were interested in was taking feedstocks that are alkaline. Take fly ashes, take slags, take alkaline rocks like basalts and gabbros, and put them in a solution. Once you put them in a solution, what comes out of all of this is you can essentially start to selectively take out all of the calcium to produce calcium hydroxide. Why is this important? If you could produce calcium hydroxide at a large enough scale with an approach of this sort, well, you can avoid the need for the high temperature activation of limestone, right? And then you can really switch towards using effectively a zero carbon feedstock for the production of cement. Keep in mind, the reason that you can do all of this, and by the way, these processes run at ambient temperature and ambient pressure, you're effectively just exploiting the pH dependent solubility of calcium hydroxide to produce it from solution, right? It comes out of solution at give or take pH 12.5, 12.7, and as I'll talk about in a second, you can do this while producing hydrogen if you use an electrolysis type of process. So calcium hydroxide is actually really, really attractive for a variety of reasons, right? Not only can it enable OPC decarbonization because you can start to eliminate the need for using limestone, but you can start to use calcium hydroxide as a cementation agent to produce concrete, right? So this is based on the carbon belt strategy. But if you take sort of a further view out, you can start to use calcium hydroxide as a low-cost sorbent for direct air capture. Turns out to be really important because if you can start to use sort of existing infrastructure that's in place to produce low-cost sorbents, this is really quite attractive because this will allow you to eliminate the need for CCS within the context of many cement plants. So an important question that really comes up is really, do you have enough calcium around? The short answer is absolutely yes. You can look at sort of quantities of slag and fly ash. There's not that much. But you know what? There's give or take a couple of gigatons of calcium in slag and fly ash around the world. The real opportunity is really around rocks. Look at pyroxenes, look at amphiboles, look at basalts and the like. There's about 200 teratons of calcium contained in just these reservoirs alone. Really important to be keeping in mind because there's lots of other things that you could be going to get calcium out of. And I think that's an important thing you want to focus on. You want to select rocks to get essentially the highest alkalinity and the highest reactivity. But the good news is once you do this identification, you've got sources of calcium other than limestone that you can start to use. So the approach that we took to this is really based on water's electrolysis, right? So you take water, you split it, run a current through water. Essentially, the cathode, you end up producing hydrogen and hydroxyl ions, and the anode, you end up producing oxygen and protons, right? Acidity. Why is this important? The hydroxyl ions allow you to increase the pH of the solution and precipitate calcium hydroxide. The acidity allows you to dissolve rock, right? So in effect, you can use just stuff that you get out of water combined with electricity to be able to produce, as an example, calcium hydroxide. Keep in mind, because you're running an electrolysis process, one of the things that's really important is you get about a megawatt hour of energy out of the process in just hydrogen alone, right? This is really quite attractive because this allows you to reduce the process's energy demand. But more importantly, if you're producing something like hydrogen, you can use it to power a traditional cement kiln. So keep in mind, effectively everything that you get out of an electrolysis process is actually really valuable because you can use all of it. So question is, does it really work? Can you really do this, right? So we've been working on this for the last several years now. We've got a pretty large pilot system running at UCLA that produces somewhere between 10 to 100 kilograms of calcium hydroxide per day. Basically, there's a couple of questions that we were trying to ask. If you look at the calcination of limestone, the energy demand for it is somewhere in the vicinity of 1.1 megawatt hours per ton, right? To go from limestone to calcium oxide. So we set that as our target basis. Can you really start to do decomposition? Can you start to do calcium hydroxide production at an energy demand that's comparable to calcium carbonate's decomposition? Okay. So we started out with really small scale systems, and what I want to show you is that we've been coming up the scale curve, but coming down in terms of energy intensity. Pretty significant reduction. So, essentially, we've managed to reduce the energy intensity by a factor of 4, give or take, from the point that we started. And the reason that is important is as you come up the scale curve, you actually make the process generally much more efficient, right? Why is that important? We're well on track to hit this number right here. We think, based upon sort of current estimates, we'll be able to hit this number on limestone's decomposition, energy intensity, at a scale of give or take 100 tons per day, right? Why is that important? Links back to an initial comment that I made around decentralized manufacturing. Can you do this with small footprint, modular, decentralized plants? The answer is potentially yes, right? I want to sort of go into closing. I've got just 2 minutes left, but really I want you to keep in mind that cement is a strategic sector, right? It provides a foundational material for our societies, and while offshoring of production might occur, border tariff adjustments will protect producers who are in low carbon jurisdictions. Keep in mind, decarbonization will be incented by strategic procurement. You can see all of these buy clean mandates that have been going out. California has one. The federal government has one. Lots of private companies are going out and doing their own buy clean mandates. And then there's direct legislation, right? So I think Tom Tietze is going to speak about SB 596 in California later this afternoon. Requires a 40% reduction in cement's carbon footprint by 2030, carbon neutrality by 2045. So you've now got a direct legislation pathway enacted into law that requires this to happen. Last thing to keep in mind is renewable energy is going to be really important, right? So keep in mind, you don't want to use renewable energy. The first use for it should be to displace fossil fuel-based electricity. After you've done that, it should all be going into process electrification for any sort of industrial system. And there's a lot of renewable energy that's going to come online over the next 20 or 30 years. And so an important question that we should be asking is, how do we make the best use of it? So really, what remains to be done? Verify the narrative, right? So we need to carefully ask the questions if we're promoting CO2 avoidance, utilization, removal, or neither. I think that's where we start. There's remarkably misleading efforts underway to suggest meaningful CO2 utilization. This is obviously a big problem, and what it really needs is uniform, robust, and transparent LCA. The problem with most LCA processes is you can game them. You can get any answer you want out of them. And so how do you really have transparent LCA is an important question. We need to distinguish between natural and accelerated carbonation. Of course, it's clear that concrete does take up CO2 over its life, but net present value accounting is super important, right? CO2 that is eliminated today is very different from CO2 that's eliminated 7 decades down the road, and we want to be clear about this. We want to keep in mind that CO2 concentration comes at a cost, and renewable energy is not free. And what this means is, as far as possible, we should be promoting utilization with the most dilute streams, but we should also be doing carbon capture with the most concentrated streams that we find. And finally, we need to focus on the development of measurement methods for CO2 uptake and reduction assessments. I don't know if Pamela Chu, anyone from NIST is in the room, but NIST has a new effort underway where they're developing protocols to be able to assess things of this sort. So really, going on to the summary and conclusions, cement and concrete are foundational materials to the world that we live in. And in spite of societal, strategic, and community value, a lot more work is needed to decarbonize cement and concrete production. This is a challenge, but it's definitely an opportunity for a once-in-a-century type of sectoral disruption. I think this is something we should keep in mind. And while there is a lot of work that's sort of started and underway, there's a whole lot more that remains to be done. And with that said, I'd like to conclude. Thank you very much.